Hey, this is Steven from RC Engineering, and welcome to the fourth week of March. And as obviously the fourth week of March, we go over a engineering concept. And today's engineering concept is rolling resistance. I also call this the rule of thumb series. So today we're going to be going over rolling resistance, which really affects land vehicles, or you could think of it also as for airplanes, it is wheels for landing gear and stuff like that also have similar principles as well. And for land vehicles, as you remember from last month on our kinematics, that it is one of the two forces that counteract your inputting energy or work to go forward at a certain high speed. So we're back on the tablet. I got my slides together, so it's way better. But we are using the mic on the laptop, so we might have some pickup from when I'm drawing on the screen. But that's okay, because I'm pretty tight on time. As you see, it's pretty close here to midnight, and I got work at the machine shop in the morning. Right, so I have a few tables up, two of my favorite, two websites. My favorite one is the Engineering Toolbox. That's my favorite one, but I also have the Wikipedia to talk a little bit about that there. So number one is this image here, but we'll go over. So again, for a car, this is mainly for cars for the most part, are the ones that mainly have to worry about this. And again, what we call free body diagram, FBD, free body diagram. What that means is we're going to look at the kinematics of the object that we want to study. So in this case, we have a little car, let's say. Right, there's our little car. And there's the wheels. Okay, so what do we have here? We have something going forward, and this is called, I guess you could say, thrust. Thrust is more for planes. This, I guess, we could just call driving force, maybe. Or I could call it a force D, force driving. Then we have two going backwards. One is wind resistance, and the other one is rolling resistance. And rolling resistance is actually another form of another resistance, which is called friction, right? So friction is, I guess, a big broad term. Rolling resistance or rolling friction, it could also be called friction, are, I guess, under one big umbrella. So there's two types. There's rolling friction / resistance, and then there's dragging. So another idea is, for example, you have a wood block on the floor, or let's say actually this is a box. Let's say, and you're going to say a box of crap, some crap that you have stored, and this box is really heavy, and here's your wood floor in the garage or wherever, and you're dragging, and you got your hand in here, let's say, and there's your hand, and you're dragging this guy this way. As you can see, it's dragging across the floor, and so friction will be back this way. But these are two completely different setups of friction. This one is called kinetic friction. Kinetic friction. Kinetic friction is when something is in motion. Another one is called static friction. Static friction is before the material starts to move. And so kinetic is already in motion, and static is not yet in motion. But the difference between kinetic friction and most of what we're going to be dealing with, because obviously this doesn't have any wheels on it. Rolling friction is when you have an object that when it's in contact with the ground, it's actually rotating. Because as you can see, this has a lot of area against the ground, while a wheel just has this section that is contacting the ground. So a wheel has a lot less friction than a box with a large footprint that's contacting against the ground. Now, that's why we invented the wheel. The wheel allows us to increase the efficiency of transportation, because regular friction, kinetic friction, for example, or we could call it from now on, we'll call it dragging friction. Dragging friction is way higher than rolling friction. So that's why we have wheels. It's able to benefit our lives drastically by the increase in efficiency, right? And now there's, but the funny thing is that the equations are very similar. The only thing that's different is some of the coefficients. We'll talk about that here in a second. Let's look through the Wikipedia here. So here you can see, you should be able to see my cursor floating around, a little white dot. This is the free body diagram. I don't know if it says free body diagram. No, it doesn't. You can see the weight here. So this is the weight of the wheel and whatever's on top of it, whatever's acting upon it. There's my cursor. Here's the force that's driving the material this way, and then here you can see this is like the resistance. And note that the R is the resultant force from non-uniform pressure at the wheel's roadbed contact surface. This pressure is greatest towards the front of the wheel due to hysteresis. So here you see the main equation. This is the force that's counteracting the movement. So if you're going forward, the force is going back. If you're going backward, the force is going forward. It's counteracting whichever way you're traveling. And the equation is F, which is your force, which is in newtons, or slugs, which is basically a pound force, sort of. And the CRR is rolling resistance coefficient, which RR is rolling resistance, or coefficient of rolling friction. And then N is what's called the normal force, which we'll go over in a second. What else does it say here? So here we have rolling resistance, otherwise called rolling friction. Is the force resisting the motion when a body such as a ball, tire, or wheel. Obviously we're talking about a tire, I guess, or you'd say a wheel, so a tire of a car, or an RC car. This is not all the energy needed for deformation or movement of the wheel roadbed is recovered when the pressure is removed. So basically what it's saying here is that it's basically the loss of energy forward, right? So you're putting a whole bunch of energy forward in the form of electric motor or a gas motor, and when this tire rotates, right, there's a pressure here, and what happens is that pressure, as it moves away, not all of it is absorbed to go back forward. Some of it is stored inside the wheel, as far as like moving air around inside the wheel, or compressing the air inside the wheel. So some of that energy is taken away. For example, let's say you have a car, an actual full-size car tire, and you have air inside that tire, right? When you compress the side of the tire, let's say if the tire's really flat and there's not a lot of air in it, when you compress the tire all the way, and you can tell it's flat, because when the car's on the ground, and when the car's flat, let's say on the surface on the road, you could tell that the very bottom side of the tire that's in contact with the road is really flat. That's how you could tell a wheel's flat. It's because the bottom of it's flat, not around the rest of this section, but the bottom's flat. So as you're moving and you have a flat tire, It's like compressing, it's constantly like moving the air around, it's circulating the air around, and that's not helping with your forward motion. So you're spending energy that you're using in gas, right, to power your car, or electric if you have a Tesla or whatever, to move that air inside the material, or to move the atoms around inside the material as well. And that's also another thing that you think about is you're stretching the material and compressing the material a whole bunch of times. Every time that thing goes, every time the wheel goes around, you're adding energy by moving those molecules around, and that energy is not helping you go forward. So it's going to a undesirable outcome, which generally is increasing heat. So it's those types of engineering losses that we're here in this series to optimize and understand. Okay, additional contributing factors include wheel diameter, speed, load on wheel, surface adhesion, sliding, relative microsliding between the contacts. So those are a few of the things. But the main thing that we're going to be looking at is the material of both objects. So you have a rubber tire. Do we have is it like a rail on a train or something like that? So let's go ahead and look at the engineering toolbox. So here again, this is I think a better document, but the other one talks a little bit about where rolling resistance comes from. Rolling resistance or rolling friction. Again, we see the free body diagram. We have weight. Rolling resistance is going backwards. Force is going forwards. So this is our free body diagram. Let's go ahead and do that free body diagram. Here's our wheel. Weight is going down this way. Force, friction, or force of rolling resistance, let's call it. And then this is force, driving force, I'm going to call it. And then this is weight. Now, let's go ahead, and they missed something that's very crucial. So you see here on rolling resistance, it says here at the bottom that the equation is force times N. N is the normal force, which is very important because those are two different equations. So what you'll see sometimes is on engineering toolbox, you'll see it as weight, and sometimes you'll see it as normal force. Basically, what the normal force is when your car is sitting on the ground, right? The wheel is not falling through the ground, right? And again, as you know, on the kinematics, we have one of Newton's laws is, I think it's the second one. I never memorized it, but if something's in equilibrium and there are forces present, which there always is on Earth, you have gravity and you have yourself. So, for example, I'm sitting right now on a chair. The reason why I don't fall through the chair, gravity's pulling on me, and the reason why I don't fall right down to the center of the Earth is because there is something pushing back. Now, in order for if forces are unbalanced, that causes movement. But currently, I'm not descending at all because I'm sitting on a chair. And same thing, just like your car. When your car sits on the street, doesn't fall through the street. Reason being is that your car's weight, which is caused by gravity, which is pulling it towards the center of the Earth, is going down this way, but yet the floor is pushing back with the same exact force to keep your car to not move, to keep it from falling down the center of the Earth. So the normal force is actually the same exact force as the weight right here, but it's just on the ground. It's the same exact size. It's the same exact, as we say, size or magnitude. It's the same number, but it's opposite in direction. It's going up instead of down. That's the normal force. So as you can see, these two cancel out, and that's why that wheel is not moving in this direction or that direction. We only have movement in this direction. These cancel out, right? So if you see it ever say normal force, that means it is what is the force that is counteracting the weight. But that is not always what happens, because if you see weight, some of the problems in engineering class, an example of why you don't want to do this weight here is because what if the ball is on a slope? Now the normal force is always perpendicular to the floor. So you see here I have a 90-degree angle between the floor and the normal force. But this wheel's weight is with respect to the world, right? This imaginary plane down here. So this is weight. This is not equal to this. This is a small fraction. Normal force is only a small fraction, because some of this weight is helping to pull it down the hill. It's helping the ball roll down the hill. So normal force is not always equal to weight. So it's very crucial. So technically this equation is wrong, because it only works on a flat surface. If the surface is angled at all, normal force is not equal to weight. Right? And then here you would have to use trig, which we'll explain later. But now we're assuming that whatever hill you have it on is flat, or there is no hill, it's flat. But watch out when you use this equation, because this weight, that's not correct. It should be normal force for N. Okay, so there's the equation. F equals CR, rolling resistance times normal force, or weight if it's flat. Now what we'll see here is we have the weight of our vehicle, whether it's a full-size car or a RC car. Then what we need to get is we need to get some of our coefficients. Now those coefficients are generally found by research, right? And what we'll see here, testing, basically testing it. Maybe one of these times I'll have to test what an actual RC car's rolling resistance is and how to measure that. So what we're going to do is we're going to look here, and we have a few rolling resistance coefficients, which is CRR. And also we have some other equations. The rolling resistance can alternatively be expressed as force rolling equals CL rolling resistance coefficient times W, which is weight, divided by the radius of the wheel. But as you can see, it only has one of those. That's just another way of solving for those in the actual testing of the testing of the wheel. So here we have railroad steel wheels on steel rails. So again, when you look up these coefficients, you have to know both materials that are in contact. For example, right now I'm wearing a pair of jeans and I'm up against a leather couch. So it's denim jeans against a leather couch. Or we could have rubber tire versus dirt, right? On dirt. So for example, if you're like my brother, he races cars at a clay track. Well, let's just say it's dirt. So it's like a bicycle tire, or low resistance tubeless tire, or bicycle tire on rough paved road, car tire on tar or asphalt, car tire on gravel, car tire on cobbles. They don't have like dirt. Bicycle tire on wooden track. Yeah, you get the idea. And then you see our resistance is over here, 0.001 to 0.002 of railroad steel wheels on steel rails. So this one would be an example of a train on steel rails. And you can see that the rolling resistance is very low. That's why a train, to carry so much weight, requires so little gas, because once it gets up to speed, it could just kind of coast for a really long time until it gets to a hill. Because again, the rolling resistance is also going to compete against the weight of pulling that train up and over the hill to increase potential energy. And then you can see how worse it gets when you have something that is loose and that moves around on sand, 0.2 or 0.4 for a car tire. So an example would be car tire. We have CR is 0.2 to 0.4, and normal force, let's say 2,000 pounds, but this is in, I think C is, so here it says dimensionless, so we don't have to worry about it, but FR is in newtons or pound force, and that's determined by, this is determined by what we say this is, either pounds or kilograms. Well, this is actually a force, newtons or force, so that would be in newtons or pound force. So let's say that is, let's say we have a 4,000 pound car. 4,000. So how many pound force? And then this is pound force. So let's pick the extreme. So that is 16,000, and then add 0.1 there. So that's 1,600. So the force equals 1,600 pound force. Now we could add that to a distance and then figure out how much work that is. So let's say that let's just do some math on here with bigger numbers than on a RC car. Actually, we'll probably do another one. Yeah, let's change it so now it's an RC car. They have one for RC car. We could just say car tire on. Yeah, we could change it so it's a car tire on loose sand. Let's just say that we're on the beach with our Praxis or whatever. So let's say we were going 25 miles an hour. That's 37 feet per second. So let's change this. Let's just say 37 feet per second. That's 25 miles an hour. Okay, so let's change this. 4,000, let's say it's 10 pounds. 10 pound force. That's 4 force. Because this is unit. So this basically is added over there. Pound force. So 4 pound force, 37 feet per second. So we need to turn this guy into work. So work is equal to force times distance. And then if distance is over seconds, that's equal to power. Power is equal to work over time. So all we need to do to get power, which is in watts, which we then could turn into horsepower. But most of what we're dealing with is in electricity. So we could do that in watts. Force, 4 pounds. Oh, but this is not going to be... We'll have to convert it from... we need to convert this into newtons. now we need to put this in meters for a second. Meters. Okay. 25 miles an hour. That's 11. That's 11.1. Sure. Okay. This is meters per second. So basically, we take the 11. So we have 18. And then we're going to multiply by a distance, which is in meters, and then seconds, which is time. This is time. So take 18 times 11. So that is a total of 198 watts that is counteracting. So if you had your little RC car, right, and you're traveling on the sand, and this is our free body diagram, you have a normal force pushing up against you from the sand. So in this case, we're traveling on flat sand, let's say. So we have our weight. Our weight is equal to 10 pound force, which this is not actually going to work. Yeah, it's okay, because we converted pound force into newton. That's fine. Yeah, it should be fine. This number seems a little high, so I might have done something wrong here, but whatever. Okay, so you get the idea. So now we're adding this force forward, driving force, and then we have a force of rolling resistance, right? And the force of rolling resistance is equal to 198 watts. So in order to go forward with a 10-pound car going over sand with this extremely high rolling resistance at a constant rate, if we were traveling at 25 miles an hour, so velocity is equal to 25 miles per hour, and we did not want to slow down, we wanted to maintain our speed at 25 miles an hour, our motor has to be at least 198 watts. Now again, this is also assuming that this is in a building and there's no wind resistance, let's say, but even at 25 miles an hour, even in a building, you're going to have wind resistance. So that one will be going over next week. Force from wind resistance. So at a minimum, you're going to need 200 watts, around 200 watts of power. Yeah. That's pretty much it. So, so you kind of get the idea, but I'm thinking that this conversion is not exactly right, because this is a lot of power. That's an eighth of horsepower right there for a 10-pound car to be going 25 miles an hour. This conversion's probably wrong, but you get the idea. So the main thing to figure out the force, and then from go to force to the power required, you need to use this equation. You need to find or test for, which I'll probably eventually do a video of testing for the CR. But what you need to do first is you need to figure out the weight of your craft, and obviously you have to figure out if it's on flat ground or not. Then you have to figure out the weight of your craft. The CR, you can either look it up, and if you're going to look it up, you need to know the material that the tire is made out of, and the material that the ground is made out of. If not, you're going to have to do, if you're going to test for it, you're going to have to do a completely different procedure. which I'm not going to go into on this video, but I'll show you guys how to do that later in another video. And then after that, you just take, let's say that you either tested for it or you found it online, and you can do the math by multiplying this guy, CR, times the weight of your craft. That is your force, and then this has to be either in pound force or newtons. Then you have to go from pound force, let's say, or what I would do is have everything in newtons. So make sure that this is in newtons here, so you can easily go to watts, because watts are newtons per second. Wait, newtons per second, newtons, newton meters per second, newton meters per second. Okay. So you end up here at newtons. That's here in newtons. Then you take to go to power, work over seconds. Work is force times distance, and then this is also known as force times velocity. Then you need to figure out what the velocity of your craft is going to be. Let's say 25 miles an hour. Convert that to meters per second. Because again, this one is Newton meters per second. So you make sure that your units make that. So this is Newton meters per second. So make sure that checks out. Then once you have that, multiply this out. Then this is over 1 second. So you just multiply your force by your speed in meters. Then you have your number of watts right here. So we got 18 times 11, 198 watts. And that is the minimum power you need for the motor. And yeah, so that's kind of the basics here for rolling resistance. Pretty easy. The hardest part of it is testing for it. If you wanted to have, if you wanted to design different types of tread of tire, you want to know how that modifies the rolling resistance, that's different. So let's say you're a big racer on a track, and you wanted to go from one tire to another. How can I measure my rolling resistance to compare, to see if it's making me slower, and etc. But again, also this leads to a different different thing as well. As you guys know, traction is also in friction. So if you apply so much force this way that the ground can't handle it, you're just going to be spinning the gravel out this way and wasting energy that way. So maybe we'll look into that into a different video. But now we're already over time here. Alright, so this has been Steven from RC Engineering. I hope you guys enjoyed this video where we're back on the tablet with the stylus. We talked about rolling friction, one of the big things to counteract cars. And hopefully next week we could go and look at the wind resistance, which is huge. Wind resistance is seen in pretty much every vehicle that you could ever build that will go fast, except for obviously something that's in space. Space has relatively low wind resistance, if pretty much negligible most of the time. So we would definitely be checking that out, because that's across disciplines for all crafts built have fluids that are running over it, air, water, whatever, of some kind or another at some point or another. Alright, so I'd like to thank you guys for watching. If you like this video, please subscribe. If you want to help me out in making my videos, go ahead and check out my Patreon. Link is in the description. I'm working on some exclusive, they're like, you'll see some exclusive footage there in these videos I call short chats, which are basically like podcasts where I talk about different RC stuff. Alright, thank you guys so much for watching. I'll see you guys in the next one. Take it easy.